Good morning, everyone. Welcome to Code Camp Bucharest. My name is Neal Ford, and I'm joined today by Mark Richards.
Welcome, everyone,
So first rule of debugging is the
There it
on
is.
switch turned on.
Hey, my name's Mark Richards. Welcome. There we go. Now you can hear me. Fantastic. Welcome to Code Camp 2024 Bucharest. So we want to talk to you today. We are replacing Venkat's talk. He wasn't able to make it, so Neal and I are going to basically show you about simplifying complexity, which kind of carries on the theme that Venkat was going to talk about. Because necessarily, in our world, we have complexity, a lot of complexity. Complexity in technology, complexity in software development, design, and even architecture. However, too many times, we tend to make things too complex. Now, this is an actual artifact of the major information flows of one of the world's largest banks. I didn't make this up. It's actually a real artifact. The question is this complex? Well, it looks complex, but we're not sure because we've made it complex. So in this session, Neal and I are going to talk about two kinds of complexity. We're going to talk about essential complexity, which means we have a hard problem. But then we're going to talk about something called accidental complexity. And this is the fact that we have made a problem hard. Now, we're going to talk about and show examples of each of these, but the main point of this session is to show you some techniques, some tools, to help address both of these kinds of complexity. So let's actually start with accidental complexity. Times when we actually take a problem and make it hard. And I want to show you a really good example of this. I'm going to show you 2 lines of Java code in a method. First one who can figure out what this does, shout it out. And here it is. Now, no, it doesn't adjust a number. It does. But more specifically, what does this code do?
Technically, it does adjust a number.
Technically, it does.
It doesn't just adjust a number.
That's right. How long do we have for this session? Well, actually,
a lot of these folks are architects, and they haven't really coded in a long time, so, you know.
Actually, we do only have 45 minutes for this particular session. It usually takes somebody 3 to 4 minutes to figure out what this code does. But I'm going to show you another method, which has 2 statements in Java. The first one who can figure out what this next one does, shout it out. Are you ready? Set, go. Yes, it doubles a number if even. Exactly.
We are at a developers conference, aren't we?
I think so, yeah. No, everybody here is Python and C# and Go and all that. No, my point is this. You really don't even need to look at the source code here. You can look at the method name, double if even. But even if you didn't trust that method name, you could read the code and it's pretty simple. X mod 2 is 0, that means it's even, double it. Otherwise, just return it. How many of you have ever written a method, go, or process, or do it? Remember the old days of do it? Neal and I are old enough, we do remember those servlet days of do it. Yes. These are ways of introducing accidental complexity. But I want to show you something really amazing. Both of these methods do the exact same thing. And as a matter of fact, we love complexity. Why do we do this top method? Maybe it's to show off that we're great in our technical skills. But do you see the implication of accidental complexity. When we make something complex, the implications of that are profound. 3 to 4 minutes to understand your code versus a couple of seconds. And that's not even trying to maintain that code. So it turns out Neal has a fantastic quote. Neal has a lot of favorite quotes of mine. This happens to be one of them.
Well, there was a book that came out a few years ago called 97 Things I think it was the architect, 97 Things Every Architect Should Know, because there were several of these 97 thing books. And the subject that I talked about was essential versus accidental complexity. And I made an observation then that has become one of my most famous quotes. And this is absolutely true, because I've noticed this for a long time among software developers, that developers are drawn to complexity like moths to a flame, frequently with the exact same results. Developers love puzzles, they love toys, and they're drawn to those things, which is great if it's a hobby, but it's terrible if it's your day job, because you end up with a just number instead of double if even if you love complexity. I actually believe some technologies exist because they loved complexity, like enterprise Java beans is a great example of something that could only have existed with complexity. And of course, this is very much this idea of accidental complexity. And even in design and architecture, we have this split. It was a book, 97 Things Every Architect Should Know, of this split between essential versus accidental complexity. And here's a great example of that.
Yeah, so I showed you some source code. We have accidental complexity everywhere in the code we write. But we also have it in design and architecture. Let's suppose we have a business sponsor, our product partner, who says, we need a system that can support 500,000 concurrent users with a high level of fault tolerance. And of course, the software architect says, yeah, no problem, I'm on it. And so that software architect chooses to use a modular monolith, a very popular architectural style. Now, a modular monolith is a single deployment unit where the structure of that system is delineated by domains. Very, very popular today. But the problem is, it's not very scalable, and it's also not very fault tolerant. So what does the development team do? Well, they take care of this by adding all sorts of internal threading, concurrency, maybe using internal messaging to get that throughput through this application, through this product. Well, it gets sort of there, but not quite. So the response, well, maybe we should have multiple instances of this system. Now we're getting a little bit better on scalability, but we still have a fault tolerance problem. Because if that database were to ever go down, the whole system goes down. Oh, I know how to fix that. Each instance will have its own copy of a database. And we'll just use bi-directional replication between these two databases to keep them in sync. This is a prime example of Neal's quote, where we've taken a problem where we're not sure if it's complex or not, and we have made it complex. Another great example of accidental complexity. Whereas, had we chosen a more appropriate architecture style, such as microservices, that has 5 stars, the highest star ratings for scalability and fault tolerance, it is true, we are adding some essential complexity, but we are significantly reducing that accidental complexity. Accidental complexity, where we make problems hard, occurs all the time. So what Neal's going to do is actually show you a tour of the other kind of complexity, essential complexity. And then we're going to switch gears and actually show you ways of tackling these problems.
We have a lot of things that are complicated in the software world without inventing new ways to make them complicated. Trust me, we have enough things to solve, enough problems to solve all by ourselves. Like, which is the appropriate architecture style to choose for this problem? I'm going to address that later today in my software architecture by example, but it turns out that almost any problem can be solved in almost any architecture style. The question is, how difficult is it to solve that problem in this style? Sometimes very difficult, sometimes much easier. That's an essential decision you have to make. Database type. Mark and I remember the days when database type was easy. There was only one kind, and you chose the red ones because they were the fastest. It was simple, but now lots of different database types with different capabilities and different trade-offs. Service granularity, which is one of the trickiest things people deal with in modern architectures, is what is the appropriate granularity for a service? Questions like shared functionality. I could either create a shared library or I could use a shared service. Which of those is better? That's an essential question you have to ask. What kind of contract? How loosely or tightly am I binding parts of my system together? More tight bindings gives me better guaranteed alignment, but it also makes things more brittle. So which one of those do I really need in my architecture more of? How do I communicate between services? Should I use blocking communication, non-blocking communication? What are the implications of that? Same for workflow. Should I use orchestration or choreography? Sometimes use one, sometimes the other. You have to do a trade-off analysis to figure out what the essence of the problem is rather than accidentally make it too complex. Same for things, really complicated things, like the finale of our hard parts book, like distributed transactions. What do you do and how do you make decisions in this space around things like distributed transactions? So that's the landscape that we're talking about. Let's dive a little bit deeper.
All right. So how do we address all of this complexity, whether it be accidental complexity or essential complexity? What we're going to do now is show you some techniques to be able to reduce or avoid accidental complexity, but also to address the essential complexity, the fact that we do have hard problems, as Neal was just showing you. All these decisions we need to make. Well, the first technique we can use to address complexity and simplify this, especially accidental, is architecture decision records to the rescue. Now, architecture decision records, or what we call ADRs, is where we make an architecture decision and we record that decision. Most of you might have heard of ADRs. Maybe some of you use ADRs, architecture decision records. But I'm wondering how many of you leverage ADRs. Because most of us think about ADRs as documentation. But they could actually be a tool, a vehicle for reducing accidental complexity and also essential complexity. The key are these sections right here. The decision section of an ADR requires us to write down our decision, but more importantly, to justify it. Why am I writing an algorithm this way? Why am I doing this kind of design, this kind of choice? And coupled with the decision part is the consequences section of the ADR, which requires us to think about and document the impact of our decision, of our actions. Let's go back to that double if even source code. If I write that really cool method with all that operator precedence to show off how much I know the language and how much math I know, if I wrote an ADR for that, or even thought about those sections, what is the impact of all that cool code? Well, the impact is everybody thinks I'm great. that's fantastic code. No, the impact is that I'm wasting all of your time trying to figure out that code, trying to read that code, maintain that code. It allows us to think about our reasons, our consequences, and justifications. And so this is a great tool. Now, a lot of you might be saying, oh, Mark, I've heard of architecture decision records. I love them, but our company doesn't use them. That's okay. I use what's called temporal ADRs. This doesn't have to be part of your company culture, your company process. There's nothing to stop you from writing your own architecture decision record to analyze your justification, to really think about the consequences and impacts, and then just throw it away. It doesn't have to exist as documentation. This is a great tool to actually leverage.
I'm just going to use this.
Okay.
Okay, I'm just going to use your.
Oh, okay.
So let's talk about. So the real job of software architects is not to find magic silver bullet solutions that solve all the essential complexity with no accidental complexity. It would be great if those existed, but they don't. Your real job as a software architect, particularly within your organization, is to be really, really good at objective trade-off analysis. That's the real job. What you need to do is, because you have the technical skills and know-how to understand the pros and cons of situations and be able to understand those in a way that decision makers can make those decisions. Very often, architects aren't decision makers, they are analysts who give information to decision makers. And this is really the life cycle of how you reconcile the trade-offs. Okay, I've done a trade-off analysis, so which one should we choose? Well, that's often not the responsibility of the architect, because you have friendly people like the stock photo who make these business decisions in your organization, and they decide things like time to market is our most important driving thing for our organization. Now, as an architect, you go and analyze the architecture characteristics and capabilities that we need for this particular system. And what you realize is that when you translate time to market to architecture capabilities, you're talking about things like maintainability, testability, deployability, because if I can maintain it more quickly, I can get new features to market more quickly. Same for testability and deployability, which are really the essence of agile software development. Now that we know what the business drivers are translated into our terms, now we can do the formal trade-off analysis to figure out, okay, what are the pros and cons, and reach a trade-off decision. Okay, in this case, it's really performance versus maintainability. One gives me better performance, the other gives me better maintainability. That's the job of the architect, and now you map that back to what the priorities of this particular problem, this particular organization or ecosystem are. Maintainability is the thing that we're interested in because that's the thing that gives us fastest time to market. Architecture trade-off analysis is really that. It's analysis, but we're trying to give enough information for informed decisions in an organization for making these kinds of trade-off decisions. So this is the first really important thing, is understand the trade-offs of a particular decision within an ecosystem like that. And that goes back to the essential complexity that we were talking about before. Like, for example, one of the things that a lot of teams struggle with is, should I break apart the service or keep it as a single thing? Because when you listen to people talk about microservices, well, microservices are supposed to be single purpose. Okay, great. So which one of these is single purpose? All notifications, or all customer notifications, or each kind of customer notification? Because I can argue over drinks that all of those are single purpose. So how do you make a decision like this? Well, what you need are tools. Mark and I are big fans of this idea of iterative architecture. The essence of agile and architecture is not the absence of architecture. You cannot build complex things without doing some planning beforehand. The essence of agile and architecture is the ability to have fast feedback loops. That's the idea behind agile, and Mark and I are big fans of applying this principle in architecture. I don't know of any architect who's so clever they can just look at a difficult problem and the perfect arrangement of components just fall out of their head onto a drawing tool somewhere. So what you need is to create a candidate and then iterate on the design. To iterate on the design, you need tools. And so that's what we're going to touch on briefly today, are some tools for iterating on granularity in distributed architectures. We have these in two different categories: disintegrators, which are tools that encourage you to break things down into smaller pieces, and integrators, which encourage you to break them, to build them back up into bigger pieces. And in our Software Architecture, the Hard Parts book, we identify 5 different disintegrators. Service functionality, let's break it down by its domain behavior and the behavior in its application. But code volatility is another one of these, because really volatile things that change a lot make terrible candidates for reuse. Because if I reuse something that's changing all the time, it's just going to drive churn in my code base, because every time it changes, I have to stop and figure out if I'm broken or not because of that change. And so volatility is an interesting way to think about separating things. Scalability and throughput, and these operational concerns like performance and scalability, elasticity. Fault tolerance and availability and reliability is another way of thinking about breaking things apart. So are things like security and access restrictions. One part of my system needs much tighter security than another part of my system, and so I may break those apart to provide different levels of security. A lot of developers sort of organically find disintegrators because it's fun to break things apart into other pieces, but then realize you also need this opposing force, this idea of integrators. And the first one of these you've probably heard about in microservices, which is database transactions. You try not to do transactions across service boundaries. For example, if you have something that you try to break apart with a disintegrator and then you realize, oh no, we're doing a database transaction, you bundle it back together and avoid that transaction. And that's a good example of this iterative nature, because you use the service functionality disintegrator and you realize, oh no, that's going to have to create a transaction. So you bundle those back together and see, is there a different disintegrator I can use for that one? Data dependencies is another common integrator. While it's simple to separate the code, it's very difficult to separate and untangle the data dependencies. And so just leave it as a single thing because of that. And workflow and choreography is another great example of this. I break things down too much, and now they have to talk to each other, and now latency and performance is too high, and I can solve that by bundling them back together. These are great examples of tools that you can use for this idea of iterative design, so that you can refine your design before you actually start writing code and spending a lot of time building something that is not the right thing to build.
That's right. Okay, so kind of continuing with this notion that to simplify some of the complexity that we do have, understanding these trade-offs really is that first step. Another complex aspect we have is with shared code. Should I use a shared library like a DLL or a jar or a gem, or should I use a shared service? Think about authorization, think about logging, auditing, metrics gathering. I mean, these are common things that we have, utilities that we use in our code. This is a complex decision. So again, understanding the trade-offs is really the first piece of simplifying this decision. And as a matter of fact, if we analyze those trade-offs, let's kind of start with the shared library. This is something that's easy to version. It's great if we've got a lot of changes. I can version it for backwards compatibility, agility. If Neal needs a change right away, I can make that. I can version that DLL or that jar or that gem, and I can have that to him in 1 hour. And I haven't broken any of you because you're using the prior version. As a matter of fact, all of the operational characteristics like performance and fault tolerance, availability, scalability, it's bound to me. I mean, this is bound at compile time. That sounds really attractive until we look at some of the trade-offs of this. Trying to manage the dependencies of shared libraries in a highly distributed architecture is a nightmare. Again, I should put the flying moth on that one, Neal. And also, if we have a lot of languages in our ecosystem, a lot of platforms, I have to write a shared library for each of those, duplicating that code across each of those platforms. These are the trade-offs of the shared library. But if we look at a shared service, where we're just invoking some service somewhere, well, the advantages here are very, very clear. If I have high levels of code volatility, if I'm changing that code often, I just change it. None of you have to do any rebuilds, any retesting, no redeployments. No, you don't even know I've been changed. That's a huge advantage, as well as the fact that I can write that shared service in any platform or language I want to. And it doesn't matter what language or platform you're in. That sounds a lot better, doesn't it? Until we look at the trade-offs, and there are a lot of them. Performance, how long does it take to get over to Neal? Because there's latency there. If I need to scale, and Neal is a shared service, he's going to have to scale as well. If Neal's our shared service, our authorization service, and he goes down, folks, all of us are down. We can't operate. Also, that change is a runtime change. So although none of you need to retest or redeploy or rebuild, I could change, deploy, and break every single one of you. It's really understanding these kind of trade-offs and what's important to us that helps reduce that complexity and allows us to make this decision. You know, a last one we'll talk about before we move on to other techniques is, in fact, choreography and orchestration. Managing workflows. Now we're really dipping into complexity. Should I use orchestration, kind of like an orchestra, a symphony where there's a conductor orchestrating all of you? Or should we use choreography, like dancers on a stage? There's no conductor there. We're just all communicating with each other. Well, this is kind of a complex decision. This is essential complexity. How do we simplify this? First step is understanding the trade-offs. And as a matter of fact, if we look at the trade-offs, orchestration gives us great management of that workflow. I understand it, it's in one place, that conductor, that orchestrator. Error handling becomes a lot easier. If an error occurs, well, you just tell me there's an error and I'll fix it. Also, recoverability. These are all great superpowers of orchestration. But if we look at choreography, its superpowers are really about those operational characteristics. Oh, things like responsiveness, availability, scalability, which we don't have in orchestration. Again, once we boil down the trade-offs, now we can ask, well, wait a minute, which one's important for my situation that we're in? And this helps simplify these kind of decisions, this kind of complexity. All right. Neal, I believe
Indeed. So let's look at the second one of our three criteria here to help understand essential complexity, and that is to apply qualitative analysis to particular problems in software architecture. I'm not sure which distributed architecture would be most appropriate for the new system. But, you know, I of an engineering mindset, and so I'm going to go to my boss and say, boss, I have good news and I have bad news. The good news is we're going to choose the perfect architecture for the new architecture system. The bad news is it's going to take me 4 times longer and 4 times as expensive as you allocated, because we're going to build all 4 of them and measure, and then we'll know exactly which one to choose. I don't think my boss is going to let me do that.
Yeah, try to sell that.
Yeah,
Yes.
exactly. So, but that's the engineering way to solve this problem, but we can't. So how do we do an analysis before we've built the thing? What I was talking about is a quantitative analysis. Build the thing and measure it and find out actual quantities. But we can't do that if we haven't built it yet. And so what we need to do is qualitative analysis. And Mark and I do this a lot in our architecture books because you need to be able to compare things together with each other. For example, of these architectures I was talking about, we built these star rating charts, 1 to 5 stars, that talk about when you compare one architecture to the other, how do they compare to each other in terms of these capabilities. And you see here the real sweet spots for microservices are things like maintainability and scalability, testability. Service-based architectures, which are a hybrid, have maintainability and cost deployability as their highlights. Event-driven architectures are really good at elasticity and scale and performance. Space-based architectures are really good at scale, performance, and elasticity as its sweet spot. What this allows you to do is to do an analysis before you write all the code to look at the magnitudes of differences between one thing or the other. And once you've done this trade-off analysis, so now we've done the job of an architect, which is do the trade-off analysis.
Neal,
now,
before you go, this looks rather complex. I mean,
It
there's
is.
a lot of stars here. I mean, we've got 5 stars everywhere, some 2 stars. I mean, this is complex.
well, how do you do the trade-off
How do we
analysis?
deal with this?
So we've done the architecture part, which is the trade-off analysis. Now we have to map it back to the decision point. How do we make a decision about this? What's really important here? Maintainability, testability, deployability. That allows us to narrow all of the differences between these things into just the things that matter in the differences between these things for this project. And this is a key part of software architecture. This is why you can't just go into an organization and say, all application development shall be microservices for now and forever. Because sometimes it's suitable, but sometimes it's just accidental complexity. It's not essential complexity, and then you start falling into the trap of all the bad things about accidental complexity.
Now that is simple.
Exactly.
go.
This is essential. It's not just simple, it's essential. It's the essential things that we need to care about in this problem.
Well, let's look at another example, and that has to do with data. As Neal mentioned earlier, there's more than just relational databases around. There are KV, document, graph databases, columnar, vector databases. How do I navigate this complex world? By the same technique. Qualitative analysis. In our book, Software Architecture, The Hard Parts, we did the same star ratings for databases as we did for architecture styles in our Fundamentals of Software Architecture book.
Thank you, Pramod Sedalge, our co-author, who is an expert in this field,
And
for
that's
supplying
right,
this information.
yes. Pramod Sedalge had actually come up with these ones. And this, again, is a little overwhelming. A lot of stars. I'm still not sure what to do. As Neal showed, we go back to our context. What's important to the business is not performance or reliability. It's getting our changes out to our customers as fast as possible. That is the goal of the business, the need of the business. So if we go now back to those star ratings, we can now use qualitative analysis and say, well, this is a little overwhelming and fairly complex. How can I simplify it? Apply our context. Because what we care about is ease of learning and ease of modeling. And now we can look comparatively at these different databases and see that, well, relational database has actually some good stars for ease of learning, ease of modeling. That's going to make things go faster, as does document databases and also NoSQL as well. These are all good choices based on the kind of data I have. But you know, there's something interesting by doing this exercise. Do you notice? What if we used a graph database? 1 star for ease of learning. There's a lot of essential complexity. Ease of modeling, only 2 stars out of 5. So what do you suppose would happen if we got all excited and started evangelizing graph databases for our solution? You guessed it. We're going to introduce accidental complexity into our system. And this really does demonstrate how accidental complexity and essential complexity really are kind of intertwined.
I can't resist just mentioning parenthetically while you have this slide up. This is the danger that many organizations fall into when they standardize on a single bit of infrastructure like a relational database. They think it's money savings. We'll pick one big giant relational database and there's just one license fee, one set of skills, and so that's a great money saving operation. But when you only have one, you have to choose the most complicated, capable one possible because it has to solve the hardest problems. And now everybody's using the most complicated, biggest database there is because you only get one. You're solving the essential complexity for a small part of your organization and creating accidental complexity for everybody else. Whereas if you chose 1 or 2 or 3 versus just one that are more suited for the problem, you're reducing the accidental complexity imposed because if you only have one, it has to be the most complicated one.
There you go. All right.
All right, let's... I don't need it.
Oh, you don't need it.
Yeah. Let's talk about quantitative analysis. I talked about actually building things. That's what quantitative analysis is. And this is something that we defined in our first edition. This is the second edition of our book, Building Evolutionary Architectures, which is coming up in a second. This idea of an architecture fitness function, which is sort of like a unit test, but for architecture capabilities, not just domain behavior. And consequently, a lot of these fitness functions need to be monitors or operational checks, not just running something at compile time. So an architecture fitness function is an objective integrity assessment of some architecture characteristic or combination of architecture characteristics. If you're going to do this qualitative analysis, then when you actually do build the thing, you should measure it and see if you were right. Because one of the things you should also do as an architect is hone your qualitative analysis skills. Because when you make guesses and hypotheses, you want to do the experiment to see how close was my guess or hypotheses, and you can refine that over time. And this is exactly this idea of quantitative analysis after the fact. Measure things like agility. So how quickly can we release things? How efficient is our releases? How maintainable is our code base? How is our testability? Are our numbers and bugs going up or down over time? These are all things that you can measure and determine from your architecture, and in fact use it to build more onto your architecture over time and get a handle on the essential complexity in your architecture.
All right, well, we have about 5 minutes left, so we have one more tip to show you to be able to simplify complexity in all of this, well, complex world. And that is, are there combinations of things that can help us simplify our decisions? And in fact, it turns out that there is. This was a discovery by Neal while we were writing our Architecture, the Hard Parts book. And it turns out things about communication, distributed transactions, workflow, turns out they are all co-joined together. And if we look at this co-joined aspect, turns out that each of these forces have a choice. Should we use atomic or eventual consistency for our transactions? Should we use synchronous or async communications? Should I use orchestration or choreography? And my head is about to explode with all these decisions and all this complexity. But because Neal discovered that these are all co-joined, it turns out there are only 8 possibilities for creating a distributed architecture with these 3 primal forces. And as a matter of fact, let's take a quick tour through these. The epic saga. These are sagas, stories, the way a transaction runs through a system using these 3 forces. We named the epic saga because this is a long-running story that seems to never end. And of course, you can see the ratings here where coupling is really bad. Remember, 4 stars is really good, 1 star is really bad. So, coupling is bad. It's simple, but responsiveness and scalability aren't good. So let's continue our tour of these.
The second one is we call the fantasy fiction story that moves communication over to asynchronous communication, and not very much good happens because of that. You can see simplicity goes way down because now I have deadlocks and race conditions, and now scalability is a little bit better, but nothing is really good here. And so this is very much something that is tempting, but probably not a great idea.
That's right. So how can we improve this? Something called the parallel saga. We take that synchronous and make it async. Again, looking at these combinations, now the parallel saga is kind of like reading multiple stories at the same time. Notice that it's now eventually consistent. The transaction boundary is around each service, not the whole entire request, trying to simulate that atomic transaction.
Phone tag saga. This is like the kids' game of phone tag with atomic consistency, synchronous communication, and choreography. This is a really weird combination, and you would not likely see this because you see terrible numbers down here for this thing, and so this would be very much an example of developers drawn to complexity because, wow, we want to use choreography for everything, but it's really unsuited for choreography, so that turns out to be a big problem.
That's right. But we can there's the moth again.
Yes, well,
Multiple.
This was the scariest one. So one of these had to be an anti-pattern, right? This is the horror story anti-pattern. This is a well-intentioned attempt to achieve atomicity at really high scale. And this is a really bad decision in architecture, but literally less than 2 months after Mark and I had come up with this taxonomy, the project I was working on, the architects brought me this pattern, and we decided not to use it because we'd figured out this is a really, really bad idea.
The ones that you see a moth flying through and burning up, don't do.
Right.
It's a great example of the combination of these forces that produce accidental complexity in your system. Time travel, a story that kind of moves through time, where you notice it's still choreography, but synchronous communication. And the best way to improve this one, if you look at the stars down here, there we go.
Anthology saga, which is much better. So
Yes.
This is a way of going through and doing qualitative analysis through an address space like this, and it allows you to make decisions in a space like this.
Well, let's close by actually showing you what is the purpose of all those 8 sagas you showed me. What's our most important characteristic? What's our most important thing we have to do? Responsive systems. We have to create the most responsive system possible. Well, how do we do that? Qualitative analysis. We look through here and say, well, the parallel saga has 4 stars, anthology has 5, which means if we want a responsive system, we know we can use the parallel with eventual consistency, async communication and orchestration, or we can choose the anthology, eventual consistency. What we have done with this tool is significantly simplified the complexity we face when trying to create these kind of systems. Listen, we have complexity everywhere in our lives, everywhere in technology, in development and architecture. Our hope is that these tools that we have shown you just make it a little bit simpler. So, thank you all so much.
Thanks, everyone.
Thank you.
Have a great conference.
Thank you very much.